So since we're using, the Laplace transform and the region of convergence to kind of help us analyze systems, it's kind of natural to ask, can we deduce from those things without actually doing a full inverse transform? If somebody just said that, the Laplace transform has poles at, well, for example, minus a half plus square root of 3 over 2j and minus a half minus square root of 3 over j. If they just told you that, can you say something about the frequency response of the system? And the answer is yes. And that's why sometimes in circuit design or filter design, you talk about pole placement to try to get certain properties of the filter. And that relates to the fact that we can geometrically evaluate. I'm writing it as h of j omega because I've been talking about a filter, but it's true of the frequency response as well. So I can write it as x of j omega from the pole zero plot. Now, so far, the zeros have had zero role in what we've been talking about, right? All of this inversion and everything, all we did was we looked at where the poles were. And the regions of convergence were kind of bounded by the poles, and the zeros are there on the sideline saying, what about me? Can I be of some use here, or am I really just a zero? And the answer is they do matter, and this is where it comes into play. So let me just give you an example, which will actually be the same one we talked about before. Let's say we look at x of s equal to s divided by s squared plus 5s plus 6, which we know we could write as s divided by s plus 2 times s plus 3. And let's look at the pole zero plot for that. Let's assume that we're looking at the system that contains the j omega axis, so it makes sense to talk about x of j omega. So we want to look at the case where the region of convergence is the real part, since the poles are at minus 2 and minus 3. We know that we're talking about the region of convergence, which is everything to the right of the rightmost pole. So the real part is greater than or equal to minus 2. What can we say about the x of j omega, the Fourier transform? Because we know it exists. So x of j omega exists. Can we say anything about it? And I should throw in now the 0 at s equals 0. Well, the answer comes from just looking at what x of j omega means. X of j omega is just x of s evaluated at s equal j omega. So I can write out what that looks like. X of j omega is x of s evaluated at s equal j omega, which is just going to be j omega divided by j omega squared plus 5j omega plus 6. Or if I want to write it in factored form, which is going to turn out to be handy, it's just going to be j omega divided by j omega plus 2 times j omega plus 3. Now, that isn't actually that helpful in figuring out I could evaluate this. I could plug this into MATLAB and say plot the magnitude and plot the phase. But you can actually figure out a few things just by looking at this and by looking at the pole zero plot. So what we'd like to figure out, we'd like to get a sense of, so I guess the way to think about it is we'd like to get a sketch of the magnitude of x of j omega. So if this were a filter, we'd be able to tell, is it a low-pass type filter or a high-pass type filter or a band-pass filter or an all-pass filter, right? You had an example where you looked at all-pass filters where the magnitude of h of j omega was equal to 1. Or if it was discrete time, the magnitude of h of e to the j omega was equal to 1. If we could somehow figure out that x of j omega was a constant, like equal to 1, we would know that it's an all-pass filter. And if it was something other than 1, we'd know it's an all-pass filter with a gain factor. And we'd also like to figure out the angle of j omega. And the way we do that is just by sort of asking, well, what do those really correspond to? So let me see. I guess I'll do let me do the magnitude over here, and then I'll do the phase on the next board. You'll have to glance back and forth, but I'll actually redraw that pole zero plot over here. So what can we say about the magnitude of x of j omega? Well, the magnitude is going to be, well, I'll just write it out. It's the magnitude of j omega divided by the magnitude of the denominator. The magnitude of the denominator is just going to be the product of the magnitudes of the two terms. And now I can sort of think about what that means in terms of the picture. So if I draw that picture again, here's my pole at -2. Here's my pole at -3. Here's the 0. And now I pick a point on the j omega axis. So now think of omega as being a particular value. What is j omega? J omega, well, it's just this point. And what's the magnitude of j omega? It's the length of the vector from the 0 at s equals 0. And what's the magnitude of j omega plus 2? Well, this is j omega minus -2. It's actually that length, that magnitude is the length of this vector. From that point j omega to the pole at -2. And this is just the length of the vector that goes from -3 up to j omega. So what is this magnitude of the frequency response, or of the Fourier transform? It's this length divided by the product of those lengths. And now you could compute it, of course, but if you wanted to just get a sense of what the nature of that response is, then what you can do is you can sort of look at certain cases. Well, one obvious case you can look at, so in other words, what I mean is we can think of sweeping omega from positive infinity to minus infinity, or minus infinity to positive infinity, and ask, how does that magnitude change? Well, as I say, you could plug in every imaginable value of omega, or let MATLAB do it, and just plot the thing. But you'd also get a rough sense of how it behaves by thinking about some of the values where things sort of have a characteristic behavior. So, for example, let's start off by looking at the large positive values. So as omega goes to infinity, so I'm moving this point up to infinity, this becomes a very long line, right? The length of this vector becomes very large. But so do the lengths of these two guys. And in fact, if you think about it, when I let omega go off to infinity, this little discrepancy down here in the base gets dwarfed. And the length of this is going to be approximately the same length as these two guys. There'll be some difference, but, this will be 1 billion or 20 billion, and this will be, 20 billion minus 1, or we can figure out from the Pythagorean theorem what it is. But it's going to be small difference. So as omega goes to infinity, the magnitude looks like approximately some large number L divided by that large number L times that large number L. It's not exactly. These are going to be a little bit longer. So I'll put like a plus there or something like that. But the bottom line is that L is going to infinity. And so it looks like L divided by L squared, which is 1 over L, with L going to infinity. Well, what does that become when L goes to infinity? 0. And it's going down gradually, right? It's looking like 1 over L. So what we know, just from that pole zero plot, is that that frequency response is going to kind of go like this. And as omega goes to minus infinity, well, it's the same story. It's just the completely symmetric picture. The same thing. X of j omega, the magnitude, goes to 0. So we know it looks like this. Now, what about in between? Can we say anything about in between? Well, when omega is equal to 0, what's the length of that? J omega. It's the length of this vector when I squish it down so it's 0. So the numerator is 0. What's the denominator? What's this length? Right? When I push this down, it's going to be that 0 length vector, its length of 0, divided by this length, which is 2, times this length, which is 3. So it's 0 divided by 6. So for omega equals 0, we get that the magnitude is equal to 0. So it's down here. Now, you could think about what happens as you approach this, and you can convince yourselves that it's kind of continuous. So it actually goes like this. And so what you can conclude just from that simple analysis kind of in the extremes and at the 0, what you can conclude is that this looks like it's bandpass in nature. It's not exactly bandpass because it's only 0 here at one point, but it's bandpass in nature. It's going to be emphasizing these frequencies and then attenuating low frequencies and attenuating high frequencies.